Okay, so our plan for today is really just to cover 3.6 solving applications with linear inequalities. Um, that'll take maybe hopefully a third or so of the class. And then for the last two-thirds or maybe a half or so of the class, I want to just go through some practice problems. Um, so basically just, putting up a few different problems that are similar applications that we've seen in chapter 3 and letting you kind of take a shot at them now that you have had a chance to, attend the lectures, to do the homeworks. Um, here's an inequality ones that'll be kind of new, but the other three, uh, you should have a pretty decent mastery of these by now. So that'll be the plan for the last half or so of class is just to take uh, a bit of time. I'll give you a bit more time than usual with kind of the expectation that you will be able to, at least for the first, third, and fourth, take everything from start to finish and feel really good about that. And then maybe get a little extra practice on inequalities as well. Okay, the quote of the day today is from the statistician George Box, and it is that all models are wrong. Oh, a typo there. All models are wrong, but some are useful. Uh, and really what he's getting at here is that when we're attempting to understand physical reality, typically what we do, as we've seen in chapter 3, we often overlay a model onto reality, and quite often that's a mathematical model. Sometimes it's a bit less mathematical and a bit more qualitative, but often it's a mathematical model when we're dealing with physical reality. And we overlay a model onto reality. And it's important to realize the hierarchy here, that the model we're overlaying is our attempt to describe that phenomenon. And it's not like force in the universe obeys F equals ma. Force equals mass times acceleration, Newton's second law. It's not that, we decided F equals ma and then the universe says, oh, okay, I'll fall in line. It's the other way around. The universe works a certain way and we say, okay, in this set of circumstances, it seems like a pretty good model is F equals ma. That seems to work most of the time in most of our experiments, and we're happy with that. It's a good enough approximation for the vast majority of purposes. And that's our model, but that model is wrong, right? F equals ma isn't the actual underlying structure. We know it doesn't work with, galaxies colliding or something where general relativity comes into play, or even special relativity for that matter. Uh, it doesn't work completely analogously, maybe at the quantum mechanical level. So it's a model. It's very, very good for the vast majority of things that we want to do in, say, engineering or something like that. So it's extremely useful. But at the end of the day, it is just a model. Now, of course, we also have models that are wrong but are not useful. Aristotle, I think, was the one who came up with F equals mv. I mean, they didn't have algebraic notation and such back in the ancient Greek philosophers' days, but he basically said F equals mv, like you need to keep pushing on something to keep it moving. And later on, we kind of realized, oh, well, it's really the force of things like friction and air resistance that are making the thing want to stop moving in some sense. So it's really a countervailing force. But so we have models that are wrong but are not useful, and models that are wrong but are useful. But at the end of the day, our attempts to understand uh, physical reality or whatever it may be are not completely correct, and we shouldn't. Uh, we should always keep in mind that these are approximations to some truth, a truth that we can't divine completely. Okay, so that is the thought for today. Right, let's look at an example in 3.6, solving applications with linear inequalities. So we have a situation here where Joni sells kitchen aprons online for $24.50 each. And the question is, how many aprons must she sell next month if she wants to earn at least $1,000? And, if we were entering this in WebAssign, we might enter the smallest such number of aprons. Why is this important? Well, uh, so why do we want to uh, round up essentially? Well, because we want to earn at least $1,000. Okay, so uh, what is my kind of strategy here? Well, let's read through. We did that. We understand the situation. We know if she sells one apron, she'll make $24.50. That's not enough. If she sells 10 aprons, about $245. Well, that's about $250 times four is 1,000. So I think she's going to need to sell around like 40-ish aprons or more. You know, if I think that she needs to sell at least 1,000 aprons, something's gone awry. And likewise, if I say that she needs to sell at least, 4 aprons, I made a mistake somewhere as well. So I think somewhere in the ballpark of 40-ish aprons is what we should be looking for as a lower bound. So let's give that variable a name. How many aprons? Let's just call that variable capital A, the number of aprons that she sells. So we want her earnings to be greater than or equal to $1,000. And I know that her earnings are going to be the number of aprons she sells, A, times the earnings per apron, $24.50 per apron. All right, that is 24.5. We don't need the extra zero at the end. 24.5A is greater than or equal to 1,000. And at this point, I have a linear inequality that I want to solve. And kind of in the back of my mind, like I mentioned, I'm thinking uh, A greater than or equal to 40-ish is what I think my answer is going to be. Somewhere in the ballpark of 40 as that lower bound. Well, I have a linear inequality, but nicely enough, it's a pretty straightforward one to solve. I actually already have my variable term isolated from the constant term. Nicely enough, my variable term also has a positive coefficient here. So I'm actually ready to go on to my last equation solving step, just dividing by the coefficient and simplifying. So the number of aprons has to be greater than or equal to 1,000 over 24.5. And I'll do this in the calculator because it doesn't seem like that's going to be a super nice answer. Oh. And that's about 41 or 40.81. So that's about 40.81. Now, here's the thing. If we look at it, if we were, being strictly mathematical about this, we could write this as our answer, or maybe something like this as our answer and be satisfied with it. If this was just a linear inequality, just an algebraic structure, but there's a context here. She's selling aprons online. How many does she have to sell to earn at least $1,000? Maybe there's something like if you earn more than $1,000, there are tax implications or something like that. So this is kind of a hard cutoff. Well, okay, she can't sell 40.81 or so aprons. She can sell 40 or 41. If she sells 40 aprons, she earns just under $1,000. 40 aprons, let's see, what would that be? 40 times 24.5, 980. Right. So selling 40 aprons is not enough for her to surpass $1,000. She needs to sell at least 41 aprons, which would be what, 980 plus 24.5, $1,004.50. So this would be our answer. In this case, we would round up and we would say the number of aprons that she has to sell is at least 41. Johnny must sell at least 41 aprons. So there are two important, and by the way, that meshes with what we expected from our earlier estimate. But there are two considerations here that I was looking at. Number one is we need to round to a whole number because of the context, right? This isn't something like how much time does somebody need to spend doing some activity? Well, time is kind of continuous, right? I could spend an hour or 2 hours, or I could break that down a little more and down to minutes or down to seconds or even down to fractions of a second. I can kind of allocate time fairly continuously. But if you sell an apron, that's kind of a discrete entity, right? You can sell one apron or two aprons, but you can't sell 1 3/4 aprons, or you can't sell 40.8 or so aprons. So I know that I need to round to a whole number. And again, kind of if we were thinking purely mathematically, we might say, well, round to the nearest whole number, right? That would be if this was just an algebraic question with no context, and we were saying, whatever, round to the nearest whole number or something, we might just round to 41 automatically. But here we actually have to think of the context. In this case, we did end up rounding up. But in another context, we might actually round down, right? We rounded up. So we got 40.81 or so, rounded up to 41. But had we gotten instead, 40.23, we also would have rounded up to 41. Because again, 40 aprons would not have quite covered the $1,000 requirement. So in this case, we decided to round up. So when we're in a context like this, especially with an inequality, we want to ask, do we need to round? If so, to what place? And do we want to round up or down, or just to the nearest, say, whole number, for instance? Often with these inequalities, we either decide from the context we always want to round up, so 40.8 or 40.2 or 40.03 would round up to 41. Or maybe we decide we always want to round down in a different context. So 40.8 would round down to 40, or 40.2 would round down to 40. We have to be aware of the context, right? If she definitely did not want to earn $1,000, if she wanted to earn no more than $1,000, then she could sell no more than 40 aprons. We'd have to round down in that case. So, okay. So let's take maybe about 4 minutes for this exercise. The algebra isn't that challenging. So the exercise is Mona's planning her son's birthday party, has a budget of $221. The fun zone charges $17 per child. How many children can she have at the party and stay within her budget? So give a little bit of thought to this. Go through, go through a bit of a scenario analysis like we did up here. So let me actually label these steps. One, go through a scenario, read through it, think of a couple of different numbers of kids and whether or not they would fit within her budget. Second, set up the equation or the inequality and solve it. So do the algebra. Oops, jumped ahead there. Third, and this is a bit tricky, actually write out. We see that we're talking about children, so we can't invite a half of a child or a quarter of a child, so we have to round to the whole number here. But write out a couple of numbers of children kind of surrounding the solution you come up with. And do you need to round up or down here? And then write your answer. So the challenging part of these couple is really the context and being really careful with the context. The algebra step 2 isn't super challenging, but take about maybe 4 minutes or so, work through this one, and then we'll come back and discuss. Yeah, is there a question? Okay, so this example, let's take a look at it. Uh, so this one actually turned out a little easier than the previous one. I usually try to make the exercises usually just a tad easier than the example we just did. And we see here that if we work through a couple of just example amounts of children, one child costs $17. So of course that's less than or equal to $221. 10 children cost $170. We're still within our budget for 10 children. So we know we can invite at least 10, but 20 is $340. That's over our budget. So our answer is going to be somewhere between 10 and 20. Right. So we could keep going and, how much do 11, 12, 13, and work our way down with trial and error. But the point here is just to get a bound on our answer, to get kind of an idea of where we think our answer ought to lie. just as a way to check ourselves at the end. So I wrote this out and then I came over here, then I returned back at the end to write that last line. Okay, so let's work on the algebraic side of things. Let's let C be the number of children that she invites, and we need the cost to be less than or equal to $221. So the cost is the number of children times the cost per child, or that's 17C, $17 per child times number of children. 17C has to be less than or equal to 221. We divide both sides by 17 to get C less than or equal to 221 over 17. And actually, this turns out to be a whole number. 221 over 17 is exactly 13. So nicely enough, we don't have to round in this example. We don't have to worry about rounding up or down. We check over here. We note that 13 children cost exactly $221, and that does satisfy the requirement that the cost is less than or equal to 221. And then we can write out our answer, something like Mona can invite up to 13 children. And it's important to note that if her budget was even $1 smaller, if it was 220 instead of 221, this would get on to 12 children, right? Even though we would get something like C less than or equal to, let's say, 12.95 or something like that. Well, if her budget is 220, inviting 13 children would cost 221. We would not round up to 13. That would cost a little too much. We would round down. So in the previous example with the aprons, we rounded up because we had aprons greater than or equal to number. Here we would round down because we have number of children less than or equal to some number. So you can think of it abstractly, that which direction the inequality is pointing is kind of telling you which way to round. But I think it's easier and maybe less error prone to think of it in context, or just to try the two ways of rounding just by trial and error and say, yeah, this one satisfies the inequality and that one does not, the original inequality. Any questions on either of these two? Okay, let's take a look at one that's a little bit more complex. Kimuya needs to earn $3,750 per month in order to pay all her expenses. Her job pays $3,175 per month plus 4% of her total sales. What's the minimum her total sales must be in dollars in order for her to pay all her expenses? Okay, so I think we get the context. We can see that so let's call the amount of sales, let's give that the variable S. If she makes 0 in sales, what is her earnings? Well, her earnings would be $31.75. And is this good or not? Can she afford all of her expenses? Is this bigger than or equal to $37.50? No. If she earns like $100 in sales, or if she makes $100 in sales, she earns 4% of that, or $4 more, $31.79, still not enough. If she earns $1,000 in sales, 4% of that would be $40. So 31.75 plus 40 is 3215, still not enough. If she earns 10,000, or keep saying earns, if she makes 10,000 in sales, she earns $400. We're getting closer. She earns $400 from the commission, and she makes a total of 3,575. Still not quite enough, but we're getting close. 20,000 in sales. For that, she would earn $800. and she'd be at 39.75, and that is above 37.50. So our answer is going to be somewhere between 10,000 and 20,000, we expect. So we kind of got a handle on the problem. We kind of, I think, understand the mechanics of how it works now, and we have a bound on our solution. Let's move into the algebraic side of things. Okay, so she needs her earnings to be at least bigger than or equal to 3,750. Now, what are her earnings? Her earnings are 3,175 plus 4% of her total sales. That's 4% times S. That's 0.04 S. And that's a letter S there. Looked like a 5 there for a second. And that has to be bigger than or equal to 37.50. This expression on the left side was really what we were using to calculate the earnings for a given sales level. Okay, so now I just have a linear inequality. I need to go through my inequality solving steps to figure out what the bounds on S are, or what the bound on S is, I suppose. We only have one variable term, 0.04S. There's no other variable term to combine with it. And now I want to work on isolating the variable term by subtracting 3175 from both sides. Here, I'm not going to get rid of the decimal because that's just going to make my other numbers a lot bigger and harder to deal with. So 3750 minus 3175. Well, 3775 minus 3175 would be 600. So I think this is going to be, what, 575. So I've now isolated my variable term, 0.04S bigger than or equal to 575. And now I want to isolate the variable itself. Divide both sides by 0.04. So S has to be bigger than or equal to 575 over 0.04, or S has to be bigger than or equal to 57500 over 4, 57,500 over 4. And I will go to the calculator to figure this one out. 57,500 over 4, 14,375. So that's the answer we get from the algebra. So I know, for instance, that 14,375 in sales yields an earnings of what we just found over there, 3750. Right, and that's the borderline case that does satisfy the requirement. We're looking for the minimum amount in dollars, and since our answer naturally came out to be a whole dollar amount, we don't need to worry about rounding. But if we were going to round, we would round up, because she would need to make a little more sales and end up with a little more earnings than required, than making a tiny bit less sales and earning just a bit less than required. So we would round up if we needed to round. In this case, we don't have to round. Turned out to be a whole number, and that's what we're looking for. Also, 14,375 is between 10 and 20,000, as we expected. So that kind of satisfies our check that we came up with at the beginning. Okay, so let's take a look at this exercise. It has a bit more going on, but it's pretty similar to some of these previous ones. It's kind of similar to this one and maybe a bit similar to the children's birthday problem one. It kind of has, in my mind, a feeling of kind of the two of those maybe a bit combined. So take a look at this exercise. Let's take about 5 minutes or so. And again, take your time working through. So I'm giving a little more time for these because, the word problems, they are a little bit more involved. So, take a few extra minutes, go through, do a couple of trial and errors. What if she does this many cuts or that many cuts? Does that satisfy her monthly expenses or not? Try to uh, get a bound, an upper and lower bound on what you think the answer is, and then go through the algebra. Uh, check and make sure the algebraic result makes sense with what with the bounds you got earlier, and um, and then also if you need to round, make sure that you round the right direction. So which direction should you round? You can try both directions and see what result that gives you and see if that is consistent with maybe how you had decided to round initially. Okay, so take about 5 minutes, work through this one, and then we will go through some practice problems just over the entire chapter 3. So we'll touch base in about 5 minutes or so. Okay, let's look over this one. So Mashti runs a hairstyling business from her house. She charges $45 for a haircut and style. We'll just call that a haircut. We'll say the number of cut and styles is just H for haircut. Her monthly expenses are $660. She wants to be able to put at least $1,500 a month into her savings account in order to open her own salon. How many cut and styles must she do to save at least $1,500 per month? Now, a couple of things here. The first we have to be careful about is we might look at this last sentence and kind of jump to a conclusion a little too quickly and think that maybe 45H bigger than or equal to 1,500 is what we need. But the thing is, that neglects the $660 from the monthly expenses. So there's actually, I think, two ways to approach this. I don't think one way is particularly better than the other. I chose one approach. If you chose the other approach, that's perfectly fine. So I looked at her total earnings. You might call this something like, gross earnings. This is like the amount of revenue, the amount of dollars that she takes in and puts in the till in the cash register, but that doesn't account for any of the expenses. So where are the expenses accounted for? In my way of looking at it, the expenses are accounted for in the needs per month. So you look at what is her earnings per month, what comes in on the plus side, so to speak, what's money coming into the business. That's 45H. And then what are the minus side things? What are the things going out of the business? Well, she's spending 660 in expenses. So maybe like taxes and rent and supplies, things like that. That's money going out of the business. But also the savings is kind of money going out of the business. It's being allocated to purposes other than the running of the business or the profit from the business. It's being allocated to savings for a future investment. So what are the needs per month? We need to cover these two expenses. Or maybe I shouldn't use the word expenses twice. We need to cover these two amounts, 660 and 1,500. So she needs to bring in 2,160 per month at least to cover those two line items. Now, just as an aside, you could have equally validly looked at this a separate way. You could have looked at this and said, well, what is her net earnings per month? In other words, her revenues, the money coming into the business minus the expenses, minus the kind of current liabilities and the things that she needs to pay right now, so supplies and rent and things like that. So you could have looked at 45H minus 660 as being like her net income. And then we need that to be bigger than or equal to $1,500 so that she's got at least $1,500 in kind of current profits each month to set aside in savings. Either way, you could have looked at it. I got 45H bigger than or equal to 2,160, which is 1,500 plus 660. Or you could have looked at it as 45H, the revenues minus the expenses, 660, has to be bigger than or equal to, that's basically the profit or like the kind of the net income, has to be bigger than or equal to 1,500. And I think you can see that these two are the same. It's just a question of which side we put the 660 on and which sign it has. It can go with the 45H subtracted off of it, or it can go on the other side, added on to the 1,500. Algebraically, these are the same, but contextually, it's just a different way of looking at it, right? Or kind of like on your paycheck, right? On your paycheck, are you going by just number of hours I work times dollars per hour? That's your gross earnings. Or are you going by like, what the check is actually for, what's going to be deposited in your bank account? Again, it depends on your perspective. For this problem, I don't think it much matters. So I went with what I thought was a bit simpler for me to do the estimate over here, I need the gross earnings to be, which is 45H, to be a certain number. But then that makes figuring out what number that needs to be a little bit more complicated. I need to add 660 and 1500 to get 2160. So if she does no haircuts, she makes no earnings. Rather than in this example, if she did no haircuts, she'd actually be in the whole 660 as far as net income, right? But here she does no haircuts, she earns no gross earnings. That obviously doesn't satisfy her $2,160 cash flow need each month. If she does 10 haircuts, that's $450, still not bigger than or equal to 2160. 100 haircuts, $4,500 does satisfy it. Half of 4,500 still satisfies it. So if I cut the number of haircuts in half to 50, that would cut her gross earnings in half to 2,250, which still does satisfy it. So up here, between 10 and 100 haircuts, I went from not making enough income to making enough. So I know the answer is going to be between 10 and 100, but I wanted to cut that down a little bit because that's quite a wide range. So I looked at 50 in between, and 50 haircuts still satisfies her her cash flow need. So the answer's got to be between 10 and 50. And we can actually just see visually, 2160 is pretty close to 2250. The answer is probably going to be around 50-ish. So coming over here, we need, at least from the perspective that I took, the gross earnings to be bigger than or equal to 2,160. Or again, if you had said that net earnings bigger than or equal to 1,500, that's fine as well. The earnings after the expenses are taken out. But either way, that boils down to the same equation. And from this point forward, we should have the same work. So if you were over here, the first thing you would do is add 660 to both sides. And then you'd end up right back at this squared off equation here, inequality here. I don't know, it's just like I say the equation so many times that it's always my like go-to. If I have two expressions related to one another, I just say equation instead of inequality. But so I probably made that mistake, a dozen more times that I haven't realized. And, just mentally, if I say equation, I mean inequality. The hazards of it being, before 10 a.m., I suppose. All right, so we should have, whichever approach you took, we should have both converged back at the point of this inequality, 45H bigger than or equal to 2160. So even if your intermediate step looked a little different than mine, that's fine. But you should have gotten back here, regardless of which approach you took. And then here we have the variable term isolated. We want to isolate the variable itself. We divide by 45 on both sides. We get h bigger than or equal to 2160 over 45. And in this case, again, that divided nicely to 48 exactly. So she needs to do at least 48 haircuts in order to afford the monthly expenses and have $1,500 for savings. Any questions on that? All right. Any questions on applications with linear inequalities at all? Any of these examples we went through? Okay, so at this point, what I want to do for the rest of the class period, so the next, I guess 50 minutes or so, is to work through these 4 problems. Probably won't take us actually all 50 minutes, but I want to give you guys a good bit of time for each one of these. And I also don't want to work through them myself while you're going through them. I want you to kind of treat this almost like a like it was a pop quiz or like you're sitting down for an exam. Um, use the materials you have on the exam. Try not to look back at your notes. But if you get really stuck, maybe look back at your notes. But also, if you get really stuck, make a note next to the practice problem and say, wait, I got stuck on this one. I need to review this topic, right? Um, at this point, you should be able to do this first one, this third and fourth one pretty confidently, right? So you should be able to work through the first, third, and fourth basically from start to finish without a problem. So previously, when we're learning the material new and we're doing these exercises, the bar is a bit lower. I'm working through it alongside you because we are seeing this material fresh, even though I'll do an example first, but the material is fresh. You haven't had a chance to go through the homework or practice the problems from the lecture or anything like that. But here the bar is a little bit higher. So at this point, especially for the first, third, and fourth, we're really assessing your mastery. At this point, you should be able to sit down and do these three. And maybe I'll put a star next to this one. This is material that we just learned today. So again, a little bit lower bar for this one. But try to work through these. And we'll take maybe it would actually take about somewhere between 8 and 10 minutes for the first one here. And then we'll come back and discuss. So this is, well, I gave you the formula here is a little bit of help and I gave you a little bit of guidance, but I want you to work through it kind of from start to finish. If you finish early, if you finish before about 8 or 9 minutes and you feel pretty confident in your answer, you've gone back, you've checked your answer, you've checked your work, then maybe move on to problem 2 and start on that one. Or if you want to, start from the bottom and work your way up, however you want to do it. But we'll take about 8 to 10 minutes for this one. We'll come back and then we'll discuss the answer as a whole after that time period. And if you have any questions, please pop them in chat. So I'm certainly not saying you're not allowed to ask questions or anything like that, just that I'm not going to work through it alongside you because I want you to have a more true understanding of, do you actually understand this material well enough to create the entire solution on your own? All right. All right. So we will touch base right around just after 9:30 or so. All right. So work on this first problem. That'll be the focus for this first time slot. Okay, about 2 minutes left or so. So just giving you a heads up, 2 minutes left. Okay, we're just a touch over 8 minutes, so let's come back together and review this first one. Does anybody want to share what answer they got, either verbally or in chat? Okay, let's work through it. So we might recognize this one. This is just kind of a reskin of one of our previous problems with slightly different numbers. So Vern sold his 1964 Ford Mustang for $60,000 and wants to invest the money to earn him 7% interest per year. He'll put some of the money into Fund A that earns 3% per year and the rest in Fund B that earns 9% per year. How much should he invest in each fund in dollars if he wants to earn 7% interest per year on the total? And again, we kind of mentioned before, conceptually, why not just put it all in Fund B and earn 9% and then you have extra money? Well, because Fund B is going to be riskier. So, typically we want to achieve the rate of return goal that we need to achieve with the lowest amount of risk possible. So splitting our money between funds A and B and achieving that 7% interest rate will reduce our risk. So Fund B at 9% would be probably a riskier investment. Okay, so let's take a look at this. Well, it's irrelevant what his name is, that he sold a Ford Mustang. The important part is that he got $60,000 and wants to earn 7%. And let's say that A will be the amount of money put into Fund A and B the amount of money for Fund B. All right, so on one hand, I know that A plus B has to be $60,000. He's splitting the $60,000 payment for the Mustang between funds A and B. So together they have to total $60,000. Okay, so the trickier equation is going to be this one here, where he puts some of the money into Fund A that earns a certain rate and Fund B earns a different rate, and he wants an overall rate of 7%. We do have to be a little bit careful here how we set this up. So let me think about what would 1 year's interest be on the investment in Fund A, on the investment in Fund B, and adding those together should give me 1 year's interest of 7% on $60,000. So 1 year's interest from Fund A would be the amount invested in Fund A times the interest rate for Fund A. So principal times rate, because we're just setting time to be 1. And that would be 0.03 A. So we take the amount that we invested in Fund A, multiply it by 3%, 0.03. That gives us 1 year's interest from Fund A. And similarly from Fund B, at 9%, that's 0.09. B is going to be 1 year's interest from Fund B. And that should be combined together. The sum of those two should be the 7% interest on 60,000. So these are our two equations. I'm going to take this second equation and maybe write it a little bit nicer. I'm going to multiply both sides by 100 to get 3A plus 9B equals 7 times 60,000. Okay, so I have one equation, A plus B equals 60,000. Another equation, 3A plus 9B equals 7 times 60,000. I have two unknowns, the amount I want to put in Fund A and the amount I want to put in Fund B. And I have two equations. This seems to be basically what I'm looking for, right? It seems like I'm ready to go with the algebra now. If I had two variables and one equation, I'd be combing through the problem statement to try to find a second equation, but I do have my two equations now that mesh with my two variables. Now I need to figure out how to combine these together to get one equation with one variable. And the easiest way to do that is just to solve one of the equations for one of the variables. So for instance, maybe A is 60,000 minus B. You could have done B as 60,000 minus A as well. Your intermediate steps would look a little bit different, but your end result should be the same. And A has to be 60,000 minus B. I can swap that right-hand side in here. So I have 3 times 60,000 minus B plus 9B equals 7 times 60,000. Let's say 9 there. I distribute the 3. I'm actually not going to multiply out these numbers times 60,000 because I see that I have a factor of 60,000 in a lot of places, and it turns out that it's going to work out a little nicer to just leave that factor of 60,000 sitting out there. Okay. So I distribute the 3. And you get 3 times 60,000 minus 3 times B. On my left-hand side, I have some like terms that can combine together. Negative 3B plus 9B is plus 6B. And now I just have number plus 6B equals number. I have my variable terms already combined together, right? There's only one variable term. So now I want to isolate my variable term. That's my next equation solving step. I want to subtract off this number from both sides. On the left side, I'm just left with 6B. And on the right side, kind of nicely enough, I have 7 lots of 60,000 minus 3 lots of 60,000. If I had 7 apples minus 3 apples, I'd have 4 apples, or 7 candy bars minus 3 candy bars, I'd have 4 candy bars, or 7 60,000s minus 3 60,000s, I have 4 lots of 60,000. So I can do this this arithmetic like this. just kind of outside of that 60,000, so to speak. So I don't have to multiply through, get really big numbers and start thinking, wait, what is like 420,000 minus 180,000? Like that's, but we could just do it this way and it's a little bit easier to manage. And then lastly, I divide both sides by 6 to isolate the variable itself. And actually, nicely enough, 60,000 over 6 is just 10,000. So B is just 4 times 10,000, or B equals 40,000. And then, of course, A plus B has to be 60,000, or A is 60,000 minus B. A is 20,000. So Vern should invest $20,000 into fund A, $40,000 into fund B. The two do add to 60,000. And well, what's 1% of 20,000? That would be $200. That will be 1 year's interest at 1%. At 3%, I would get $600. So let me write that up here. So 0.03 times 20,000 is going to be 600. And what's 1% of B? Just move the decimal place 2 to the left. That's $400. What's 9%? 9 times $400 is 3,600. And what's 7% of 600,000? Well, that's, sorry, 7% of 60,000. That's 7 times 600, 4,200. 3,600 plus 600 is indeed 4,200. So I see that this choice of A and B also satisfies that interest, that 1 year interest equation. So we've checked, this does satisfy both equations, and this is how Vern should split his money to achieve the goal that, for whatever reason they decided, 7% interest was what the goal was. Any questions on this one? How did you feel about this one? Did this feel, it shouldn't have been easy. It's certainly not an easy problem, but it shouldn't have been insurmountable. If you did find it insurmountable, go back and take a look at this problem that we did in a previous lecture and, some similar problems, maybe review that homework set. But if you felt pretty confident with this one, then thumbs up. This might not be a topic that you need to spend a bunch of time reviewing. Okay, let's look at the inequality one next. We'll have to speed up a little bit. We're running slightly short on time here. So inequality one next. Let's do about 6 minutes for this one, I think. One note on this one, be really careful with, this is dollars and this is cents. Be really careful with your units here. We'll take about 6 minutes, just like before. I'm not going to write steps along the way. Try to go through this. This is newer material. We did just cover this in lecture today, but see if you can go through this and, refer to your notes minimally. Try to work your way through it and get the answer, check the answer, just to see how well you understand this concept. So we'll come back in about 6 minutes or so and work through the answer. Okay, just about 2 minutes left. Okay, let's work through this one. Anybody have an answer they want to share? All right, so let's work through the answer then. All right, so Rahul and Claudia decided that to save money, they would move themselves from their apartment to their new house. They had to rent a truck to do this. Their budget's very strict. They could afford to spend no more than $200. So the cost has to be less than or equal to 200. The truck costs $46.50 per day, $46.50 per day, and 26.5 cents per mile, or a fraction thereof. If they decided they would need the truck for 2 days, what's the maximum number of full miles they can put on the truck? So what's the cost? It's going to be 2 days at $46.50. So this is in units of dollars. We have less than or equal to 200. That's in units of dollars. So plus the mileage fee. Let's say that M is the number of miles they put on the truck. I might be tempted to write 26.5 M here, but that would be the number of cents, right? If I did 26.5 M, this is in cents, while the other term in that expression is in dollars, and the other side of the inequality is in dollars. So I really need to think of 26.5 cents is 0.265 dollars. So now this is denominated in dollars. So that was the first kind of tricky part about this. Um, I gave you a little bit of warning about that, but we had to be sure that all of our units meshed nicely together. Okay, at this point, I have a linear inequality in one variable. Let me multiply out this first term here. So 2 times 4650, well, that's 80 plus twice 650. So I think that is 93 plus 0.265 M less than or equal to 200. I have my variable terms combined together, or really only started with one variable term. I need to work on isolating my variable term. I subtract 93 from both sides and get 0.265 M less than or equal to 107. So in other words, they have $107 left over after kind of the flat rate daily fee for 2 days to pay for the mileage on the truck. How many miles can they buy for the remaining $107? We divide both sides by 0.265. I haven't really explicitly been stating this, but since we're dividing by positives, by positive numbers in all of the examples we did, we're not worrying about flipping the sign. But of course, if we were dividing by a negative number, we'd have to flip the sign. But we have 107 over 0.265. And I came out with approximately m less than or equal to 403.77. So they have to drive less than or equal to 403.77 full miles. Now we might say, we might be tempted to say, or whatever, at most 404 miles, rounding 403.77 to the nearest number of full miles. But note that if they drove 404 miles, that would put them just a touch over their $200 maximum. So actually we need to round down. Round down. So they can drive at most 403 miles. So 403 miles in addition to the 2 days at the flat rate will bring them in just under $200 for the total. 404 miles, if that mile gauge, ticks over to one more mile, that will put them just over the $200 they had decided was their limit. Okay. Any questions on that? As a little side note, again, all models are wrong, some models are useful. In a situation like this, are they likely to quibble about a few cents this way or that way? Probably not, right? If they went 404 miles, it's not disastrous. But on the other hand, so there are some practical situations where the limit's more of a soft limit. If you're plus or minus one or something, it's not a big deal. On the other hand, there are examples where the limit is a much more of a hard limit, right? If you have whatever 2 problems you need to complete for an exam or 10 problems you need to complete for an exam or whatever, how much time do you have per problem? And well, if you're 1 second over on the completion of that problem on an exam, it's going to say on an online exam, it's going to auto submit before you get to enter that answer. You get 0 points for that problem, even if you've completed it 97% of the way. You need to actually complete it, get the answer in under the time limit, or it will auto submit. So there are some problems where such a limit is much harder, and other problems where such a limit is a bit more malleable, where we can be a little more flexible in our result. But really, we want to answer the proper way, regardless of how hard or soft that limit is. So we do want to say they can drive at most 403 miles. And the problem statement gives you a little bit of a hint there as well. Round down to the nearest whole number. And that is why we're rounding down. Okay, so the good news is that those were the two, definitely the 2 more challenging problems of the 4. For these last 2, let's knock them out in the same little session here. We'll take another, maybe about, let's say about 5 minutes. That'll bring us to 10:02, and then we'll have plenty of time to review them. So we'll take about 5 minutes for these 2 problems, work through these 2 on your own. Again, try not to use previous notes. Try to, use it as a self-assessment. At this point, you should have pretty good mastery of this material for these 2. So take about 5 minutes. We'll touch base at about 10:02 and go through the answers to these, and that'll wrap up our meeting today. Okay, it's just about 10:02. Yeah, exactly. So somebody just posted in the chat for the latter problem, use a squared plus b squared equals c squared, the Pythagorean theorem. Exactly. Um, so let's just work through these two in our last couple minutes here. So Brian borrowed a 10-meter extension ladder to use when he paints his house. If he sets the base of the ladder 6 meters from the house, how many meters up the side of the house will the top of the ladder reach? So we can draw a little like diagram here. Here's our house. And whoops, the ground, which hopefully is kind of flat, not like my drawing. We're going to assume that the house meets the ground at 90 degrees. This is one of those problems where we have to kind of add in a reasonable assumption that the ground is horizontal and the side of the house is vertical. Of course, if the side of the house was leaning for some reason, or if the ground was, if the house was kind of built into a hill and the ground was at an angle, that would make this a more challenging problem. And we have our ladder. We know the length of the ladder is 10 meters. And he's setting the base of the ladder 6 meters from the house. That's this distance. And we want to know how many meters up the side of the house will the ladder reach. Let's call this point where the ladder reaches to, let's say that that's h meters off the ground. Everything's in the same units. And I see that I really just have a right triangle here where the hypotenuse, the side opposite the 90-degree angle, is of length 10. The base is width 6, and then we have a height here. And our Pythagorean theorem says a squared plus b squared equals c squared, where the one that's by itself is the hypotenuse opposite the 90-degree angle. So here that means h squared plus 6 squared equals 10 squared. Now, again, we haven't talked about solving quadratic equations yet, but this is actually a pretty straightforward one to solve. We basically just have a variable term plus a constant term equals another constant term. Let's get the variable term by itself by subtracting 6 squared from both sides. H squared is, well, 10 squared is 100, minus 6 squared is 100 minus 36, I think is 64. And here we can just ask ourselves, well, what number squared gives me 64? That's got to be 8. So the height of the ladder will reach, even though it's a 10-meter ladder, because we have to kick the base out, we can't just put it straight up against the wall and climb up it. It'll fall backwards. We have to kick the base out 6 meters. So we are only actually able to reach 8 meters high on the house. So we need to decide if that's enough or not. Right? If we needed to reach higher than that, we would either need to accept a a, a smaller, bump out from the house. We'd have to go fewer than 6 meters out from the house. Either that, or we would have to get a longer ladder. Or we could probably, take two ladders and tie them together if you've ever seen those crazy YouTube videos of people doing stuff that it's like, I don't know how you've made it to that age doing these kind of things, but kudos to you, I guess. So that is our geometry Pythagorean theorem problem. And then the last problem, not really an application problem, or not a word problem, but a percent application problem that's a little more, a little kind of closer to the algebra, so to speak. 4.8% of what length is 17 inches. The is indicating equals, and the of times. So 0.048, let's call the length L. 0.048 times L equals 17. And we see this is a pretty simple equation to solve. We just divide both sides by 0.048. And that gave me the L was either 21.25 divided by 6, or L is approximately 354.2 inches. Okay. So we can either take the 17 over 0.048, make it 17,000 over 48, and then divide by 2 a bunch of times, 3 times, and get 2,125 over 6 as an improper fraction, that many inches, or we can get approximately 354.2 inches. So it's really 354 and 1/6 of an inch. Any questions on anything that we talked about today? Any of the practice problems, did these feel comfortable? Did they feel challenging? If a couple of them felt comfortable, but maybe one or two felt really challenging, maybe that's an indication you might want to go back and review those topics that you found challenging. Especially for things like word problems, things like applications. We have a lot of different formulas just to be comfortable with, um, and just being really diligent about reading the word problem carefully, understanding exactly what information it's giving you, what it's asking for, and how everything fits together. Any questions from today? Okay, then let me stop the recording.